All right, so let's take our understanding of intermolecular forces and apply that to liquids. Some properties of liquids first. Viscosity is the resistance to flow. Things that are more viscous tend to be kind of thicker looking. They don't flow as fast. Think about maple syrup is a rather viscous liquid. Molasses is even more viscous. So viscosity is related to intermolecular forces. The stronger the intermolecular forces, the more viscous the liquid. Also, viscosity increases with larger molecules, again, because of stronger dispersion forces and lower temperatures. So, for example, maple syrup will pour a lot easier, a lot faster if it is heated up than if it is cold. And so just make sure you understand that relationship. Another property of liquids is something called surface tension. This is the inward force that must be overcome in order to expand the surface of a liquid. You probably have experienced the high surface tension of water if you've ever done a belly flop into a swimming pool. Um, the surface of water is almost hard if you think about it. If you slap your hand on some water, it's going to hurt, again, because those particles are all held tightly together across the surface because of the strong intermolecular forces between the water molecules. Take a look on page 457. We see some examples of surface tension. Um, we also see at the bottom of the page examples of cohesive versus adhesive forces. Cohesive forces are forces of attraction between different things. Cohesive forces are forces of attraction between the same things. Adhesive forces are forces of attraction between different things. So we have a couple examples at the bottom. You have liquid water and liquid mercury. The water molecules are actually more attracted to the glass than they are themselves. That's why we get a meniscus, and the kind of edges of the water pull up. This is a pipette, I believe, here. Pull up on the sides of the pipette. Whereas mercury actually has stronger cohesive forces. It's more attracted to each other than to the glass, and so we get kind of that convex meniscus for mercury. And this is also related to capillary action. So capillary action occurs when the molecules of a liquid are attracted to the interior walls of a glass tube. So all of these things are kind of related to each other: viscosity, capillary action, surface tension. So they all have to do with the attractive forces between the particles. So maybe if you've ever had a finger prick where the doctor or nurse had to take some blood from you, they put a small tiny hole in your fingertip, and then they take a very narrow glass tube and stick it on that drop of blood, and the blood just goes up the tube by itself, goes up through capillary action because the blood is attracted to the whatever the glass is made of. The book it shows primarily silicon dioxide, and so pulls the liquid right up with it. So that is called capillary action. Next up, we have evaporation. I should say maybe and vaporization. So vaporization is a general process where something turns into a gas. Either a solid turns into a gas in the case of sublimation, or a liquid turns into a gas in the case of either evaporation or boiling. So let's talk about evaporation. Again, this is a process where a liquid changes into a gas. This process occurs below the boiling point of the substance. So that's very important to note about evaporation. Also important about evaporation, it occurs when the molecules at the surface escape the liquid and become a gas. So how does this happen? The molecules at the surface, if they possess enough kinetic energy, they can break free of their attractive forces and become part of the gaseous phase. So molecules at the surface experience less attractions than, say, molecules in the middle of a liquid. The molecules in the middle of a liquid are surrounded by other molecules, whereas the molecules on the surface are only held by the molecules next to them and below them. And because of this, the molecules on the surface are able to move around more easily. And if they get moving fast enough, they can break free of their attractive forces. Liquids, as you probably know from experience, evaporate faster at a higher temperature. So again, we're looking at the kinetic energy of the particles. If you increase the kinetic energy of the particles, this will allow them to then uh, escape the liquid state and become a gas. So take a look at the bottom of page 458. This is a kinetic energy distribution curve. So what it shows is that there's a minimum amount of kinetic energy required for a liquid to evaporate. And if you heat up a liquid, you increase the number of particles that have enough energy to break their attractive forces. Therefore, that liquid is going to evaporate faster. So that also is very important. Rate of evaporation versus temperature. A little vocabulary term, condensation is the opposite of evaporation. So condensation involves a gas turning into a liquid. So if you were to take a liquid and put it in a container and close that container, first of all, the liquid would evaporate because all liquids evaporate all the time. Secondly, though, the particles in the gaseous state would actually rejoin the liquid state, so you'd have some condensation that occurs as well. In fact, a point is reached where the rate of evaporation is equal to the rate of condensation if you have a liquid in a closed container. So the liquid will continuously evaporate, the vapor will continuously condense, and at that point we call this a state of dynamic equilibrium that has been achieved. So you have two opposite processes occurring at the same time and at the same rate. All right, some more vocabulary. Vapor pressure. First of all, again, vapor is the gas produced by a liquid that evaporates, or the gas produced by, the gas produced when a solid sublimes. So either way, so vapor pressure happens to just be the pressure of that vapor. And so it's important to understand what affects the vapor pressure of a liquid. It's not in the notes, but we'll add it. The vapor pressure of a liquid is related to attractive forces. So the stronger the attractive forces between the particles of a liquid, the less that liquid evaporates. So it's harder for a liquid to evaporate. And because of that, you're going to have less particles in the gaseous states and a lower pressure. So stronger the attractive forces, the lower the vapor pressure of that liquid. Vapor pressure is also related to temperature. So as temperature increases, the rate of evaporation increases, more particles in the gaseous state are produced, leading to a higher pressure. So I'm going somewhere with this. So I just want you to understand what vapor pressure is and the factors that affect vapor pressure. Vocabulary term we saw in one of the book questions, volatile or volatility refers to how easily vaporized a liquid is. So liquids that have weak attractive forces will again evaporate readily. And so we will say that they are volatile. So volatile, sometimes people think means explosive. That's not necessarily the case. So a liquid that's easily or readily evaporates is volatile. A liquid that readily evaporates must have relatively weak attractive forces. Of course, the opposite's also true. Any substance that has strong attractive forces will not evaporate very readily, will not be very volatile. All right, take a look on page 459. So this is what I was talking about before. So we have vapor pressure of some different substances at different temperatures. Let's take a look at water. So water has hydrogen bonding. We see as the temperature of water increases, so does its vapor pressure. Just below that is benzene. Benzene is a nonpolar molecule, experiences just dispersion forces. And so we can see that the vapor pressure of benzene is significantly higher than water at any given temperature. Again, this is due to the weaker attractive forces. Any guesses what kind of attractive forces methanol has? Look at the vapor pressure of methanol. Methanol actually has hydrogen bonding, but it's a rather volatile liquid. So the hydrogen bonding in methanol is not as strong as a hydrogen bonding in water. That is why methanol has a higher vapor pressure than water at a particular temperature. And then we have diethyl ether, which has dipole-dipole forces. Ethanol and methanol, the difference is just the carbon chain. So notice that ethanol has a lower vapor pressure than methanol at any given temperature, um, except for 75 degrees Celsius, it looks like there is higher, telling us about, again, the relative strength of the attractive forces between the particles. All right, turn the page, figure 1313 at the bottom of the page. Again, something else I was kind of alluding to. So this is a very common graph, a graph of vapor pressure versus temperature. So we have three different substances there. This is probably one of the most common graphs of this. Diethyl ether, ethanol, and water are shown here. So again, diethyl ether exhibits dipole-dipole forces, ethanol, hydrogen bonding, and water, hydrogen bonding. And so we see that at any given temperature. So let's say, oh, I don't know, 40 degrees Celsius. How do the vapor pressures compare? Well, water has the lowest vapor pressure at 40 degrees Celsius. Can't tell from the scale, but it is really low. Lower than ethanol. Ethanol at 40 degrees Celsius looks to be maybe a little less than 100 torr. And then 40 degrees Celsius looks like the diethyl ether is close to 1,000 torr. So again, vapor pressure is related to strength of intermolecular forces. We'll talk about boiling next lesson, but notice too, it gives you the boiling points, the normal boiling points of those substances. So there's a relationship between vapor pressure and boiling. So we'll talk about that next time.